we're going to continue today with thermal chemistry. Remember, heat chemistry. And we're going to talk about what they call enthalpy. Okay, it's a process whenever there's and again, we have to be at constant pressure so we don't figure that in. So we're talking about basically atmospheric pressure when we're on the Earth or on the surface of the Earth. The only work that's done by pressure then isn't involved in it, but instead we have to worry about heat flow. Okay, and entropy is actually measuring the heat flow in a system. Okay, and I don't know why it's H. I suppose because energy is probably E. I don't know, but enthalpy is H. And there's an H right there, I guess. I don't know. But enthalpy is the heat flow through a system. And you see the way to figure it out. E is energy, pressure, volume. Okay, so it's the internal energy plus the pressure and the volume. Okay, so this is the internal energy, this is pressure, volume, and that's going to equal H, which is enthalpy. Okay, later on we're going to talk about entropy. I know, crazy, right? But enthalpy is the internal energy of a system. Okay, so when a system changes at constant pressure, the change in enthalpy, which is delta H, remember, anytime you have a triangle, that means delta, and it means change in. The change in enthalpy is right here. The change in the internal energy plus the pressure volume, those you add together, and then that's going to give you your change in enthalpy. Okay, they also write it like this. Let me see. Okay, the reason I whipped through that other one, you don't need that equation because it's just showing you how we change it and change it. But this is what we're really looking for. The change in the internal energy is going to be Q, which is the heat lost or gain, plus the work. Okay, or work is going to be, again, using that other equation, is going to equal this. So if you just substitute everything in, what we really need is this one right here. Okay, so all those other equations, let's just worry about this one. Okay, so I know in math you always worry about getting it down to it and remember now. We're just going to worry about this one in the end. So the change in H equals Q. And if you remember when we did specific heat, Q is the heat lost or gained. Okay, because again, there's not going to be a lot of change in pressure and volume when you were working at the same level. So the volume and the pressure stay the same. So our change in enthalpy is going to equal the heat lost or gained. Okay, so at constant pressure, the change of enthalpy is heat. I just said that, huh? I must have been psychic there and learned my stuff. But again, Q is the heat lost or gained by a system that's listed in joules. And we did that before we did with specific heat. We said specific heat was the mass times the change in temperature times whatever the specific heat was for, like water was 4.184, metals were like less than 1, that kind of stuff. Well, when you calculate that, you also calculate the change in enthalpy. Okay, so when we're talking about endo and exothermic, we talked about those before. Endothermic means it's gonna, the system, now this is the system. And again, remember, some people think like this whole inside of the safe is the system. It's not. This right here, just the reaction itself is the system. Okay, all the rest of it is surroundings. Okay, so we got surroundings here and surroundings here. Okay, so if the system itself, the reaction gets colder, which means it gains heat. I know that sounds weird, but it's sucking heat from the environment, so it gets cooler out here because this guy takes it in. Okay, because when you put a thermometer in here, you're still getting the surroundings. You're not getting the actual in the equation. And I know it took me a long time to, I was like, that doesn't make sense. But when we're doing these, when we're measuring the temperature, we're measuring temperature surroundings. So if the surroundings is getting cooler, okay, that means you're gaining internal energy. All right, so the temperature is going to go down because this guy is sucking in the energy. So when we take temperature, we're doing out here. Even though we stick it in there, it seems like we are, but we're still getting out here. Okay, so the heat gained in that our bag of gold, right? The heat gain, that would be an endothermic reaction because it's going to increase. Okay, so the process is endothermic when delta H, when the enthalpy is positive. When the heat is actually gained, not lost. Okay, the process in here now, again, we're losing stuff here. Okay, it's releasing heat into the environment, And that's why when we take the temperature over here, it gets hotter. And most of the reactions that we do, most of the stuff we measure in chemistry, especially in the labs, is going to be exothermic. Most of the reactions we do are exothermic, okay? There's a lot of endothermic too, but they're just not as common, okay? Excuse me. So delta H would be negative, okay? The change in internal energy, the enthalpy, is going to be negative if it's endothermic. If it's positive, it's exothermic. I mean, say that one more time. Reverse that, okay? Strike it and reverse it, as they used to say. If delta H is negative, it's exothermic. That means it's going to have a negative number when we talk about the internal energy. If delta H is positive, the enthalpy, then it's going to be an endothermic reaction. In other words, it's going to be a positive number, okay? Okay, here's an enthalpy of a reaction, okay? We're going to figure this baby out. All right, here we have a balloon that has hydrogen and oxygen gas in it, okay? And you can see if you light it on fire, kaboom, right? So this quantity, this change in enthalpy for a reaction is the enthalpy of a reaction or heat of reaction. They all mean the same thing, okay? So if it's a violent reaction like this, we know it's definitely exothermic. So we know this is going to be a negative number, okay? We actually know the numbers for these and we can calculate it. And that's kind of what we're going to do today. So when you have a reaction, you can actually calculate if it's endothermic or exothermic, okay? Okay, so some of the things to remember about enthalpy. First of all, it's weird because it's an H, okay? But it's an extensive property, which means it depends on the amount of substance you have. Okay, if you have 2 moles versus 1 mole, it's going to be a larger number. Okay, so it's extensive property. The amount that you have changes the enthalpy, the change. The enthalpy change for a reaction is equal to the magnitude. Okay, so how big the reaction is, but opposite in sign. So if you have a big boom, it's going to be a negative number. Okay, if it's not, it doesn't seem very, reactive, you're going to have a positive number. And I know that seems kind of weird, but again, remember, we're talking exothermic is a negative number, and exothermic is where we've got, anytime you burn something, it's exothermic. So it's going to have a negative number. Okay, and the enthalpy change for reaction depends on the states. Okay, gases are have much more changes in enthalpy than liquids or solids. Actually, I don't even think you figure solids into them. Okay, so the states of the reactants and the products makes a big difference. Gases are the big ones as far as more changes. They affect it way more than like a liquid or a solid. Okay, all right, to figure this out, we can use something called calorimetry. If you look here, we have a thermometer that goes down and these are just styrofoam cups, you guys. You put 2 styrofoam cups together, you're going to have air in between, and that's an insulator. So you can have a reaction that occurs in here, okay, and we can measure it. And if we were doing these labs, we are way cooler than this thermometer. We have something called LabQuest, and it's a digital. You put it in there and you set up the machine, and it reads the temperatures and records them for you. And they're all digital. You don't have to sit there and go, what does that thermometer say? Yeah, so it's kind of nice if we got to do them, sorry. But since we cannot know the exact enthalpy from the reactants and products, we can measure it through one of these. This unit is called a calorimeter, and basically it's set up to keep as much heat in as possible. Yeah, you're going to lose a little around here and a little around here, so it's not perfect, but it's close enough, okay? You have a stir, keep it up, and again, these are just styrofoam cups that keep in the energy, okay? The instrument that uses to measure this is a calorimeter. That's how they figure out the calories in your food. They burn them in a calorimeter, okay? We were going to do a lab, and again, I'm babbling, but we would have done a lab where we would have burned food, not in a calorimeter though, just out in the open, and measured how much it increased the temperature of water, and then we could have figured out. It wouldn't have been perfect, but it would have given us an idea of the calories in food, okay? Okay, so when we're talking about heat capacity and specific heat, again, specific heat, here's the numbers for specific heat, and the largest is water. It's very, very important to us that water has a large specific heat, because what it means is water absorbs heat and it hangs on to it, okay? If you don't hang on to the heat like water does, when the sun goes down, we freeze to death. So we really, really like water holding on the heat, okay? It holds the heat, and then at night it releases the heat and keeps us more, normal temperatures, more so we don't have such radical, like really hot during the day and really cold at night. Okay. So the amount of energy required to raise the temperature of a substance 1 degree Kelvin or 1 degree Celsius is its heat capacity. Okay. And we call that specific heat because we talk about specific heat. It's just taking the heat capacity and just talking about just 1 gram. Okay. If we're doing 1 mole, it would be its molar heat capacity. So, they're all just conversions. But this is the one we really count on as water. And you can see metals are really low. They don't hold on to heat. They're conductors. They allow heat to flow through them. Okay. So we've got the next highest is methane, which is a gas, and it holds on to heat. But, look at water. Ice, even solid water, even holds on to heat. Its specific heat is like 2.87, I think. I can't remember. But it's, near 3. But again, that's really important to us because we like not to freeze to death at night. You know what I'm saying? Okay. So if we have a calorimeter set up again, okay, we're going to carry out a reaction in an aqueous solution in water. And what we're going to do is we're going to record the temperature of the water, and then we're going to have a reaction occur, and then we're going to record the temperature of the water, and the water is going to be the one that's going to tell us that change in temperature, okay? We can just measure the heat change in the water, and then we would take that change in temperature times its specific heat times how much water we have, and that would give us a change in heat. Okay? So again, the specific heat for water is 4.184 joules, grams, Kelvin. And again, when we're figuring this out, we need the amount of water we have and the change in temperature. That's the Kelvin. We can use Celsius too, either or. And then joules, remember, is our energy. So when we're done, the grams are going to cancel out. The Kelvin is going to cancel the temperature, and we're going to have joules, and that is our unit of heat energy. That's how we'll find our enthalpy. Okay? So to calculate it, this is what we do. All right? We take, If we want to figure out the heat, okay, what we're going to do is we're going to take the specific heat. And again, specific heat is C. Sometimes you'll see CS, sometimes you'll see CP. Depends on what book you're in. But this is a specific heat, so we'd use this, 4.184. Again, there's a chart in your book that has all the specific heats for many of the substances. So we know water is 4.184, and that's the one we most commonly use. The mass of the water, okay, and the change in temperature. Okay, so we're going to measure the temperature before and the temperature after. The change in temperature is what's going to go here. And again, when you're using calorimeter, you can use Celsius, you can use Kelvin, because they're going to be, the only difference with the Celsius is you'd have to change it by adding 273 to it. If you want to change a Celsius to a Kelvin or subtract 273. And if you're doing gases, you definitely have to do that. Okay, oops, I'm sorry, you guys. Got a little crazy with my thing. All right. So that's, specific heat is going to, if we want to find the heat lost or gained by a solution, okay, we're going to take the specific heat, again, which is usually water, 4.184, times how much water we have, the mass of the water. The nice thing about water is if we had 50 milliliters, that'd be 50 grams because they equal each other. And then we're going to measure the change in temperature before and after our reaction. Okay, they have something called bomb calorimeters. They're really cool because what they do is they have the reaction in there, and you can see this is really sealed up. And then you ignite it by like adding a battery. Here's you got your positive and negatives. You stir it up a little bit too. But these are really cool because they're, they go like a bomb. We don't have any of those, you guys, but we did this once at NDSU. It was pretty cool. And this would give you a better idea. This is how they really measure like the calories when you burn corn flakes or whatever. This is where you get a better idea of the calories. But so this is a fancier calorimeter. And it's called a bomb because it's really sealed, and they hit that reaction and you get a little in it. So I guess that's why they call it the bomb. The heat absorbed or released by the water is very good. This is much more, this is a fancier machine. It's going to be more accurate because it doesn't have as many places for heat to escape. But for us, 2 styrofoam cups works great. It's not really that far off. It amazes you. But you still do the same thing. You record the temperature before and after. You record the amount of water that you have. And we know the specific heat of water is 4.184. So we can figure out how much this reaction, how much heat it released. Okay. Again, we would figure that out in our bomb calorimeter. Okay. So because the volume of the bomb is constant when it's measured, it's really a change in internal energy, our change in E. not a change in H, but it's close enough. The difference is so small that it's close enough. And we're just about out of time, so that's where we're going to end today. Okay.